Welcome to Unit Number 2, Introduction to Thermal Engineering of Systems and Mechanical Engineering subject, first year, all branches. In this lecture, we are going to see some details about the thermal engineering, the basics of thermodynamics. Thermodynamics is a science of energy transfer and its effect on various physical properties of matter. Thermodynamics is mostly concerned with heat and its conversion into work. So we are going to deal with heat and work transfer to each other in thermodynamics subject or in this chapter. Now, the content of this chapter are laws of thermodynamics, heat engine, heat pump, refrigerator, and the numericals based on these three topics. Modes of heat transfer, just like conduction, convection, and radiation, and some laws related to heat transfer, that is Fourier's law, Newton's law of cooling, Stephen Boltzmann laws, and the simple numerical based on these three laws. Then we are going to see two-stroke and four-stroke engines, petrol, diesel, and CNG engines, and steam generators in the third part of this unit. Now we'll see some definitions, classical definitions and other of thermodynamics. Thermodynamics may be defined as it is an axiomatic science which deals with the relations among heat, work, and properties of system which are in equilibrium. It describes state and changes in state of physical system. Or we can define as thermodynamics is a science of the regularities governing processes of energy conversion, or it is a science that deals with the interaction between energy and material systems. Some definitions related to thermodynamics. One, that is system. In our study of thermodynamics, we will choose a small part of the universe to which we'll apply the laws of thermodynamics. So you can see here, this system is bounded by one boundary. We call this subset as a system. In this system, we have taken a small part of the universe and we are going to apply the laws of thermodynamics. Now surrounding the rest of the universe outside the system, close enough to the system to have some perceptible effect on the system is called as surrounding. The surrounding will have some effects on the system, and that's why the surrounding which is nearest to the system is called as surrounding. Boundaries, the surfaces which separate the system from the surroundings are called as the boundaries as shown in figure. For example, walls of the kettle or the housing of the engine can work as a boundary of the system. Types of system, we can see here, closed loop system is there. So what is the definition? In which no mass is permitted to cross the system boundary. That is, we would always consider system of constant mass. So you can see here, observe here in the diagram, that is, mass cannot be transferred due to this lead of the burette, but heat can be transferred inside out or outside. So this is called as a closed system. We do permit heat and work to enter or leave, but not mass. So here heat can be permitted, but mass cannot be permitted to move from system to surrounding and surrounding to system. Now the second, that is open system, in which we can allow mass as well as heat transfer, in which we permit mass and heat to cross the system boundary in either direction, from the system to surroundings or vice versa. In analyzing open system, we typically look at the specified region of the space and observe what happens at the boundaries of that region. Most of the engineering devices are open systems. Now, the third type of system is a isolated system, in which there is no interaction between system and the surroundings. It is of fixed mass and energy, and hence there is no mass and energy transfer across the system boundaries. Just like a thermos flask, in which we do not allow heat transfer as well as mass transfer from the boundary. So in open system, there will be more mass transfer as well as heat transfer. Both will be there. In closed system, there will not be a mass transfer, only heat transfer is allowed. And in isolated system, no mass transfer, no heat transfer. Now property. The thermodynamic property, the physical entity which gives information about thermodynamic system is called its property. For example, pressure, temperature, volume, internal energy, enthalpy, entropy, and heat capacity can be called as thermodynamic property. Intensive properties, the thermodynamic properties which do not depend upon mass within the system are called as intensive properties. Examples are pressure, temperature, density, coefficient of linear expansion. All specific properties, that is property per unit mass, and molar, that is property per unit mole properties, are intensive properties. The examples are specific volume, specific enthalpy, molar heat capacity, universal gas constant, because they are per unit mass or per unit mole, so they do not depend on mass. Extensive properties, the thermodynamic properties which depend upon mass within the system are called extensive properties. For example, volume. Volume depends on mass, internal energy depends on mass, enthalpy, entropy, and mass itself depends on mass. So these are extensive properties. Now, how we can bifurcate extensive and intensive property easily, that we'll see in this example. Suppose we have one system with mass, volume, temperature, pressure, and density. And if I will put a boundary in between, the mass will get half, volume will get half, but temperature will remain same, pressure will remain same, and density will remain same. So extensive properties are which are changing with mass. And intensive property, that is, there will be no change with changing in the mass. That will be your intensive property. This is called as partition method for identification of intensive and extensive properties. You can remember it easily. State and state postulate. State of system, a complete set of all properties of system under given condition is called state of a system. For example, consider air inside a closed room as system. The air will have definite value of temperature, pressure, volume, internal energy, and so on. A collective set of all those values is called as state of a system in that condition. Now we will consider that there is slightly change in temperature or pressure, then that state will change. So change in one state variable, that is property, is sufficient to change state of a system. Okay, so suppose in the room 18 degrees Celsius temperature is there, and you started a heater, room heater, and it elevated its temperature to 21 degrees Celsius. So the state of the system will change irrespective of pressure, volume, internal energy. All things will change automatically, but only one state variable is sufficient to change the system. State postulate: for homogeneous single phase system, only two independent state variables are sufficient to determine all remaining state variables. So they are interdependent, and if we can define only two independent variables, they are sufficient to determine all other variables. The word equilibrium implies a state of balance. In an equilibrium state, there are no unbalanced potentials or driving forces within the system. Now, there are four types of equilibrium. First is thermal equilibrium. There will be no change in temperature within the system. Mechanical equilibrium, there will be no change in pressure within the system. Chemical equilibrium, there is no change in chemical composition within the system. And the last one, that is thermodynamic equilibrium. If all above three equilibriums coexist together, then system is in thermodynamic equilibrium. Now you can see here the process, that is one state has been changed to other state with the help of a process path with the help of two properties. So process is defined as any change that a system undergoes from one equilibrium state to another. This one equilibrium state to another state, and this is called as a process. And the series of states through which a system passes during a process is called as path of the process, this process path. Isothermal process, no change in temperature. So if there is no change in temperature, then we call it as isothermal process. Isobaric process, no change in pressure. Bar itself is a unit of pressure. So if it is isobaric, then there will be no change in pressure. Isochoric process, no change in volume. Core is nothing but volume. So there will be no change in volume. And adiabatic process, no exchange of heat between system and surrounding. Reversible process. A reversible process is a thermodynamic process which, once having taken place, can be reversed by slight change of driving potential, and while doing so, the system undergoes through exactly same states as that of forward states. So in reversible process, the process path will be followed as it is. The necessary condition for reversibility is equilibrium. There has to be equilibrium within the system and in between system and surrounding during the process. So total path should be in equilibrium. Then only reversibility happens. In order to achieve equilibrium, the process must be slow. Hence, reversible process also known as quasi-static process. Quasi-static is the meaning that is it is likely static process. After reversing the process, the system as well as surroundings will return to the same original conditions. All real life processes are actually irreversible, but still we study reversible processes because some real life processes can be closely approximated by reversible processes. For example, expansion of steam turbine. Work producing devices such as steam turbine produce maximum work, and work consuming devices such as compressor consume least work if all processes are reversible. Hence, engineers try to strive for reversible process. Reversible processes are easier to analyze, and that's why we like reversible processes. But in real life, there are irreversible processes. The process, once having taken place, cannot be reversed to its original state without leaving any traces on surroundings, is called irreversible process. The system will not go through the same state during forward and reverse process. Factor responsible for irreversibility. First one, that is friction. Because work done against the friction is in forward cannot be recorded in reverse process. And friction occurs in every phenomena. Condition of non-equilibrium, because the total path will be in non-equilibrium state. Heat transfer through finite temperature difference. And the last, that is a mixing of two different gases. That's why the processes are irreversible. Now, in next lecture, we are going to study zeroth law, first law, second law, and all these numericals based on these laws. Till then, thank you. We'll meet again in the next.